It is 3 a.m. Your PagerDuty is screaming because your application's core feature is dead. OpenAI's GPT-4o is returning 503 errors globally, and your code has client.chatCompletions.create hard-coded across 20 different microservices. You realize you are completely stuck. There is no fallback, no retry logic that matters, and no way to switch providers without a full code deployment and a multi-hour CI/CD cycle. In the field, we see this brittle dependency pattern everywhere. Developers treat LLM APIs like a local database that never fails, but in reality, these are external services subject to regional outages, model deprecations, and sudden quota changes. If you hard-code a single provider's SDK into your business logic, you have built a house of cards that will eventually collapse under production pressure. This lecture is about ending that fragility once and for all. By the end of this course, you will know how to build a production-grade routing layer that survives provider meltdowns without a single line of application code change. Let's look at the architectural failure points that lead to this disaster. When we talk about infrastructure resilience, we usually focus on Kubernetes or multi-region databases, but in 2026, the LLM provider is the most volatile part of your stack. The promise of an LLM gateway specifically utilizing tools like LLM is to decouple the intent of the LLM call from the implementation of the provider. Instead of your application code specifically asking for GPT-4o, it should request a high-reasoning class model with a specific latency target. The gateway then handles the messy details of authentication, load balancing, and switching to Anthropic Claude or Google Gemini if the primary choice is unavailable or slow. This abstraction isn't just a luxury, it's an architectural necessity for any team that wants to scale beyond a simple prototype. Think of it as a load balancer specifically designed for intelligence. But is downtime the only thing we should be worried about? Actually, there are 4 other massive risks hiding in your direct integration code that will drain your budget before you even notice. The first major risk is vendor lock-in. If you use the OpenAI Python SDK directly, switching to a more cost-effective model like Llama 3 on Grok or a fine-tuned model on Azure requires significant refactoring. In a production environment, that's a week of work you can't afford. There's the rate limit wall. Every provider has quotas. Once your app scales, you'll hit tokens per minute limits that throttle your growth. A gateway allows you to spread load across multiple accounts or even different providers seamlessly using a round-robin or priority-based strategy. We also see maintenance debt. Managing different auth patterns and response schemas for 5 different providers in your backend logic is a nightmare. By standardizing on an OpenAI-compatible gateway interface, you simplify your entire stack and make it future-proof. But don't think for a second that just avoiding outages and lock-in is enough. The real pain comes when you look at your monthly cloud bill and the time to first token metrics across different regions. Direct calls prevent you from performing global optimization. When you call an LLM directly, you're blind to the cost-performance trade-off happening in real time. For example, during peak US hours, maybe an AWS Bedrock instance is 20% cheaper or 100 times faster than a direct OpenAI call in your region. Without a routing layer, you can't capture that value. You're also missing out on semantic catching, the ability to serve the same response for similar prompts, with even hitting the provider, which can save thousands of dollars and reduce latency to near zero. In the field, we call this cost volatility. A gateway gives you the control to enforce cost caps, and automatic model downgrades for non-critical tasks. This is how you run AI at scale without going bankrupt or frustrating users with 10-second wait times. Now that we've identified why the direct approach is a ticking time bomb, it's time to look at the blueprint of the solution. We're going to dive into the actual components of an LLM gateway in the next chapter. In a messy production environment, your application code often becomes a spiderweb of different SDKs. You have OpenAI's library here, Anthropic's over there, and maybe a custom LangChain wrapper somewhere else. This is a maintenance nightmare. When you architect an LLM gateway, the first priority is establishing a unified API. Think of it as a central post office. Your application sends one standard request, and the gateway handles the protocol translation. Whether the downstream is a REST API or a specialized gRPC stream, the gateway masks that complexity. In real-world systems I've seen, this single change reduces the time to market for adding a new model from weeks of refactoring to just a few minutes of configuration. But how do we transform these different shapes without writing spaghetti code for every provider? The secret lies in strict standardization. Question is simply passing through the data enough. Let's see why it's not. When we talk about standardization, we aren't reinventing the wheel. The industry has effectively settled on the OpenAI chat completion schema as the de facto protocol. An LLM gateway acts as an abstraction layer that allows your backend to speak one language. Tools like LLM or similar proxy solutions take a standard messages array and map it to Anthropic's human assistant format or Gemini's content structure automatically. This includes handling the nuances of streaming. Different providers use different server-sent event formats, but your application only sees one clean stream. If you've ever tried to debug why a specific version of a model suddenly changed its response envelope, you'll know why this layer is a lifesaver for stability. Teaser standardizing the input is only half the battle. Where do we put the eyes and ears of our system? In a production environment, I don't know why it failed is an unacceptable answer. A gateway gives you a single point to attach observability tools like Prometheus, Grafana, or OpenTelemetry. Instead of logging into 5 different provider consoles to find one error, you see everything in one dashboard. You can track token usage per user, per department, or per model in real time. This is where you implement structured logging, capturing not just the prompt and response, but the latency of each hop, the cost of the transaction, and the specific version of the model that handled the request. When a user complains about a weird response, you have a complete trace from the gateway to the provider and back. Payoff. Now that we have a central pipe for traffic, let's look at how we can get smart about which way that traffic flows. Not every prompt needs a 100 billion parameter model. Sending a hello or a simple yes no classification to GPT-4o is a waste of money and increases latency. This is where semantic routing comes in. The gateway acts as a traffic controller. We can set up policies. If a prompt is classified as easy by a smaller model like Llama 3AB, we route it to a cheap provider. If it's a complex reasoning task, we send it to Cloud Opus. This logic stays in the gateway configuration, not in your code. You define the what, the policy, and the gateway handles the where, the model. This approach can cut your LLM bills by 40% without sacrificing quality. Question: cost optimization is great, but what happens when a specific model starts lagging or hits a rate limit? In a high-scale production environment, relying on one endpoint is a recipe for disaster. We need load balancing, but LLM load balancing is different from traditional web balancing. Traditional round-robin doesn't account for the fact that one model might be throttled or experiencing high-tail latency. A smart gateway uses weighted distribution or latency-aware routing. For example, you might have 3 different Azure OpenAI deployments across different regions to bypass individual quota limits. The gateway monitors the liveness of each. If US East 1 starts returning 429 too many requests, the gateway immediately shifts the weight to US West 2. This happens transparently to the user. Teaser load balancing keeps us fast, but what about the legal and physical constraints of where our data actually travels? Data residency and sovereignty are huge hurdles for enterprise AI. Some of your customers might require their data to never leave the EU, while others prioritize the lowest possible latency from Tokyo. Regional routing in the gateway allows you to tag requests with geographic requirements. You can compare US-based endpoints, which often get the newest models first, against local regional endpoints that offer better data compliance and lower speed of light latency. By managing this at the gateway level, your application remains region agnostic. This architectural foundation is what enables true production resilience. We've built the brain of our LLM infrastructure. Now it's time to put it to work. Bridge. In the next chapter, we will dive into the actual implementation of multi-provider fallback to ensure your app never goes down. In a real production environment, calling LLM APIs directly from your application code is a recipe for disaster. When you scale, managing multiple SDKs for OpenAI, Anthropic, and Google becomes a maintenance nightmare. This is why we use a centralized gateway like LLM Proxy. By wrapping the gateway in a Docker container, we create a unified, OpenAI-compatible entry point. This allows your backend services to remain provider agnostic. They just send requests to a single internal URL, and the gateway handles the complexity of API key rotation and request signing. I've seen teams struggle with hard-coded keys in environment variables across 50 different microservices, which is a massive security risk. Centralizing this via a proxy ensures that only the gateway needs access to the high-privilege keys. It's the first step to moving away from implementations toward a robust, enterprise-grade architecture. But wait, simply having a proxy isn't enough. The real power lies in how we configure the routing logic inside. Now, let's look at the heart of the gateway, the config YAML file. In a production setting, you should never expose the actual provider models like GPT-4o 2024 or 2013 directly to your front-end or mobile app. Instead, we define a virtual model name, let's call it production GPT. This virtual name maps to a list of actual model deployments. This abstraction is critical because it allows the DevOps team to swap out the underlying provider without changing a single line of application code. If GPT-4o starts having latency issues in a specific region, you can update this YAML file to point production GPT to a different endpoint or a fine-tuned model on Azure. This mapping layer gives you the agility to respond to provider price changes or performance degradations in real time. But what happens if the primary model in this list returns a 500 error or hits a rate limit? This is where the strategy field becomes your best friend. Question: do you know the difference between weighted shuffle and less latency routing? We're about to define how the gateway chooses the winner. Static mapping is great, but the real world is messy. API providers go through brownouts where they don't fail completely, but start timing out or throwing 429 rate limit errors frequently. To handle this, we implement a circuit breaker pattern and robust retree logic. You don't want a single slow request to hang your entire user session. By configuring num retries and retree policy at the gateway level, we ensure the system tries again with exponential backoff before giving up. More importantly, the gateway can temporarily trip the circuit for a specific provider if it sees a 50% failure rate over a 10-second window. This prevents your system from pounding a dying API and instead shifts traffic to healthier alternatives. In silos, individual developers might implement their own retry loops, leading to retry storms that make outages worse. Centralizing this logic ensures a coordinated response to failures. But wait, retrying the same model isn't always enough. Sometimes the entire provider is down. How do we switch to a completely different LM family automatically? The golden path of LM engineering is fallback chaining. Imagine your app uses GPT-4o for complex reasoning. If OpenAI goes down, you don't want a service unavailable screen. You want to fall back to Claude 3.5 Sonnet, and if that also fails, to Gemini 1.5 Pro. We code this sequence directly into the fallback list. The gateway will transparently attempt each model in order. This is a game changer for SLAs. I've seen production uptimes jump from 98% to 99.99% just by adding a fallback to a secondary provider. However, keep in mind that different models have different prompt sensitivities. Your system prompt might work perfectly for GPT but fail for Claude. This means your gateway configuration needs to be paired with robust prompt engineering. It's not just a technical switch, it's a functional one. Now that we've secured the connection and handled failures, we needed to talk about the elephant in the room, cost and latency. Teaser, how do we prevent these fallback calls from doubling our monthly bill? Next, we tackle caching. Every token you send costs money, and every millisecond your user waits decreases engagement. The most effective way to optimize both is through caching. We implement a Redis-backed caching layer at the gateway level. For repetitive queries like common customer support questions, we don't even need to hit the LLM. If the exact same prompt comes in, we serve the result from Redis in 5 minutes instead of waiting 2 seconds for an API response. But the real senior move is semantic caching. Instead of looking for an exact string match, we use vector embeddings to see if a semantically similar question has been asked before. If a user asks, how do I reset my password, and another asks, tell me the steps to change my password, a semantic catch can recognize they are the same intent. This can reduce your API costs by up to 30% in high-traffic applications. However, catching introduces the challenge of stale information. You must decide on a TTL time to live that balances freshness with performance. Let's see how we configure this at the gateway. In production, unlimited is a dangerous word. Without strict budget limits, a single buggy loop in your code or a malicious user could burn through your entire monthly API budget in hours. A good LLM gateway allows you to set granular quotas. You can set a daily dollar limit for the entire organization, or more importantly, per user or per API key limits. For example, you might allow a free tier user only 1,000 tokens per day, while a pro user gets 100,000. Implementing this at the gateway level is far superior to doing it in your app code, because it provides a centralized dashboard for financial oversight. I've seen horror stories where a developer's test script ran overnight and cost $5,000 because there were no guardrails. By setting a max budget and budget duration in LLM, the gateway will automatically block requests once the limit is hit, protecting your company's bottom line. But cost control isn't just about limits. It's also about optimizing the content that we send. Question: are your prompts carrying unnecessary token weight? Before a request even leaves your gateway, you have one last chance to save money: prompt optimization. Every character in your system prompt and every turn in your chat history counts toward the input token cost, which is often where the bulk of the bill comes from. In the gateway, we can implement a checklist of pre-processing rules. For instance, trimming excessive white space, truncating long chat histories based on a token window, or stripping out unnecessary metadata. If you're using few-shot examples, are you sending 10 examples when 2 would suffice? Another major optimization is context pinning or prompt catching features offered by providers like Anthropic and OpenAI. The gateway can intelligently flag specific parts of the prompt as statics, so the provider can catch them on their end, leading to significant discounts on repeated context. This is the difference between a junior developer who just sends it and a senior engineer who curates it. This checklist should be your Bible before going live. But how do we know if these optimizations are actually working? We need numbers. To wrap up this chapter, remember that you cannot manage what you cannot measure. A production gateway isn't complete without a real-time observability dashboard. You need to track P99 latency across all providers simultaneously. If GPT-4o's P99 latency spikes above 5 seconds, your routing logic should automatically start bleeding traffic over to Claude or Gemini. We monitor success rates, token usage per model, and total spend in real time. This data isn't just for the engineering team. It's for the product and finance teams to understand the ROI of AI features. We've covered the how-to of implementation, from Docker setup to fallback chaining and catching. You now have a resilient blueprint. But even the best architected systems can fail in unpredictable ways when things get truly messy in the real world. Payoff up next, I'm going to share some war stories from the field situations where even our failovers failed and what we did to survive the outage. See you in the next chapter, Production War Stories. In theory, adding a fallback provider like Claude 3.5 Sonnet to your OpenAI integration sounds like the ultimate safety net. However, in a high-traffic production environment, I've seen this backfire spectacularly. Imagine your primary GPT-4o tier handles 500 requests per minute, RPM. Suddenly, OpenAI experiences a regional outage. Your LLM gateway instantly routes all 500 RPM to your fallback provider. But wait, did you check your quota on the secondary provider? Often, teams keep a free or low-tier account as a backup. The secondary provider, built to handle only 50 RPM, is immediately crushed by the thundering herd of redirected traffic. Within seconds, your fallback is also returning 429, too many requests errors, creating a cascading failure that brings down your entire application. This isn't just a theory. It's a common oversight in multi-LLM architectures. You haven't built a resilient system. You've just built a more complex way to fail. Think you're safe just because you have a set API key? You might just be moving the fire to a much smaller room with no exits. To prevent the thundering herd, we use a strategy I call shadow warming. You cannot treat your fallback providers as cold spares that sit idle until a crisis hits. In a production gateway setup, you should constantly route a small percentage of shadow traffic, perhaps 1% to 5% to your secondary models even when everything is healthy. This serves two critical purposes. First, it keeps your provider quotas warm and allows you to negotiate higher limits with the provider based on actual usage history. Second, it provides real-time latency and reliability metrics for your backup. If the secondary provider is already slow or unstable, you need to know before the primary fails. In 2026, Multi-LLM allows for weighted routing where you can define these percentages easily. By the time a real outage occurs, your infrastructure is already limbered up to take the hit. But even with warm quotas, what happens when the backup model returns data in a format your parser doesn't expect? Let's look at the hidden danger of model discrepancy. One of the most frustrating war stories I've encountered involves response discrepancy. Even if you use a unified gateway like Multi-LLM that maps everything to an OpenAI-compatible JSON schema, the underlying models are fundamentally different. For instance, when you request a JSON response, GPT-4o might be strictly compliant, while a fallback to an older Llama 3 instance via a different provider might wrap that JSON in triple backticks or add introductory text like "here is the JSON you requested." If your application code isn't robust enough to handle these formatting quirks, your fallback will technically succeed at the API level but fail at the application level by breaking your JSON parser. I've seen entire pipelines crash because a secondary model used a different key case or omitted a required field. You must implement aggressive post-processing or use Pydantic-based validation at the gateway exit point to ensure the shape of the data is identical across all providers. Schema issues are annoying, but state issues in a multi-turn conversation are catastrophic. Let's look at why stateless gateways often fail here. When we talk about stateful gateways, we're entering the realm of complex multi-turn conversations. Most developers treat LM calls as stateless: send a prompt, get a response. But what happens if a user is mid-chat and your gateway decides to fail over to a different model for the third turn? If the new model has a different context window size or handles system prompts differently, the conversation's vibe and quality can shift abruptly. Worse, if you're using sticky routing where a user session is tied to a specific provider for consistency, your gateway must maintain that state. A naive stateless gateway will treat every request in a thread as an isolated event, potentially bouncing the user between 3 different providers in a single session. This leads to disjointed experiences and debugging nightmares. To avoid this, we need the gateway to be aware of the session ID and ensure that if a switch occurs, the entire conversation history is correctly reformatted for the new provider's specific quirks. Maintaining the stickiness across a cluster of gateway instances requires more than just a local cache. In a modern Kubernetes-based production environment, your LLM gateway won't be a single instance. It will be a distributed cluster of pods. This brings us to the challenge of distributed locking in global state. If pod A thinks you've used 99% of your OpenAI quota, but pod B is unaware and keeps sending requests, you're going to hit hard rate limits and crash. Multi-LLM handles this by integrating with Redis for global state management. By setting a Redis URL, all gateway nodes share a centralized counter for rate limits and a shared cache for prompt results. This prevents the split-brain scenario where different parts of your infrastructure have different ideas about provider health. Without this, your failover logic becomes a game of chance. You must ensure your Redis instance is as highly available as your gateway, or it becomes the very single point of failure you were trying to avoid. Even with a synced state, how do you know the provider is actually healthy before the request fails? The final piece of the war story puzzle is defining health. In the old days of REST APIs, a 200 OK meant you were good to go. In the world of LLMs in 2026, a 200 OK is just the beginning. I've seen scenarios where a provider is healthy according to HTTP status codes, but the time to first token, TTFT, has spiked from 200 mems to 10 seconds. For a real-time chat app, that's a functional failure. Your gateway needs to perform advanced health checks. It should monitor tokens per second TPS and latency percentiles. If a provider's P99 latency exceeds a certain threshold, the gateway should soft fail and route traffic elsewhere, even if no explicit error was returned. We also check for degraded reasoning. Sometimes models return short, repetitive nonsense when under extreme load. A robust gateway monitors the response length and repetition penalty flags. Now that we've survived these war stories, it's time to codify these into the actual best practices and anti-patterns we'll cover in the next chapter. In production environments, I still see teams hardcoding OpenAI or Anthropic API keys directly into their service environment variables, or even worse, in plain text configuration files across multiple microservices. This is a massive anti-pattern. When a provider rotates a key or you hit a rate limit, your entire application requires a full redeploy just to update a string. A 2026 best practice is offloading all credential management to the gateway layer. Your application should only talk to the gateway using a single internal bearer token, while the gateway handles the complex rotation and provider-specific keys securely in an encrypted vault or secret manager. If you are still passing individual API keys in every function call, you are creating a huge attack surface. Centralizing this is not just about convenience. It is about security and operational agility in an era where model providers are fragmented, but security is only the first hurdle. What happens when your solution to these problems actually makes your application feel slower to the end user? Payoff. I have seen teams build gateways that are heavier than the LLM inference itself. They add nested middleware for complex logging, multiple regex-based content filters, and synchronous database writes for every single request. By the time the request actually reaches the LLM provider, you have added 500 milliseconds of overhead. In the field, we call this latency bloat. Every millisecond matters when you are trying to stream tokens to a user. Your gateway should be a thin, high-performance proxy, not a monolithic business logic layer. Use asynchronous logging to external syncs, prefer Redis for catching over disk-based databases, and keep your routing logic a 1. If your gateway does not respond in under 10 to 15 milliseconds for a catched hit, you are doing it wrong. The goal is to provide stability and observability without sacrificing the magic of real-time AI. But how do we scale this globally when users are spread across different continents? Question. By 2026, the standard architecture has moved away from a single centralized gateway sitting inside a private VPC. We are now seeing the rise of edge gateways. Imagine running your gateway logic on edge nodes like Cloudflare workers or globally distributed serverless functions. This allows the gateway to handle caching and initial routing as close to the user as possible. If a user in SOL requests a summary, the edge gateway checks a local regional cache before even hitting the US-based model provider. This edge-first approach reduces the time to first token TFT by hundreds of milliseconds. It also allows for regional failover where you can route to a local instance of an open-source model if the global provider is congested. This isn't just a luxury anymore. It's the blueprint for enterprise-grade AI that needs to feel instantaneous. However, speed is useless if the model's output quality has degraded during the routing process. Teaser. The final piece of the 2026 puzzle is in flight evaluation. High-performing teams are no longer just monitoring simple metrics like latency and error rates. They are monitoring quality in real time. This means the gateway occasionally pipes a sample of responses to a smaller, faster judge model, often an optimized ABB parameter model check for hallucinations or formatting errors. If the quality score of a specific provider drops below a certain threshold, the gateway automatically adjusts the routing weights to prefer a more stable provider. This creates a self-healing AI infrastructure. We are moving from static routing to quality-aware routing. Integrating these automated checks into your gateway ensures that your fallback logic doesn't return a fast answer, but the correct answer every single time. This completes our look at the modern blueprint for LLM operations. Now, are you ready to put all these pieces together and achieve that elusive 99.9% uptime for your AI services? Next, conclusion, your path to 99.9% to AI uptime. In the real world, you cannot simply flip a switch and migrate your entire production traffic to a new gateway architecture overnight. I have seen countless teams break their systems by trying to rip and replace direct SDK calls. The journey to 99.9% to uptime begins with a phased migration. Start by deploying your light Elm or custom gateway in a shadow mode. This means you send a duplicate of your production traffic to the gateway but ignore its response, using it only to validate latency and routing logic. Once you are confident, move to a canary stage where only 5% of traffic flows through the gateway. In 2026, the standard is to decouple the API key management first, then the routing logic, and finally the observability layer. By the time you reach 100% of traffic, you should have a kill switch ready for each provider. If OpenAI goes down, your fallback logic should have already been tested in this staged rollout. This isn't just about code. It is about building confidence in your infrastructure 1% at a time. But as a technical migration, all you need to stay ahead in this volatile market. Not quite the true mindset shift is what separates the masters from the amateurs. As we wrap up this journey, remember this one hard truth from the field. In 2026, LLMs are no longer special or magical utilities, they are volatile infrastructure components. Thinking that one model will always be available or that prices will stay static is a recipe for disaster. Experience shows that the most resilient teams are those that treat LLM providers like raw commodities. Your gateway is your insurance policy against vendor lock-in, sudden API deprecations, and regional outages. Don't just build for the happy path where the API returns 200, okay. Build for the 1% of time when everything fails. High availability isn't something you add later, it's a result of how you handle failures today. By implementing the fallback patterns, semantic caching, and unified routing we discussed, you're not just writing better code, you are ensuring your business survives the AI winter or the next major outage. Treat your prompts as code, your models as disposable workers, and your gateway as the central brain of your AI operations. This is how you achieve that elusive 99.9% to uptime in a world of probabilistic outputs. I hope these field-tested patterns help you build something truly robust. Now, it is time to take these blueprints and turn them into your production reality.